Director of Science for the National Math and Science Initiative, and I am really glad that you are here. This is yet another installment in working retired AP Chemistry stoichiometry problems, and this particular one has a unique twist in it because in the middle of it, it goes into a freezing point depression moment. It's not a comment on the psyche of freezing points everywhere. It's just a technique that is no longer on the redesign. All right, so I'm going to do this in a table format where I have my C, my H, and my O, my carbon, hydrogen, and oxygen. And in the first list, I'm going to put their molar masses. So 12.01, 1.01, and 16. So what am I doing here? I am going to make the calculator do all the work. I'm going to make it more visual for you. I'm showing you what you would write down as your answer. So in my L2, I'm going to put in the amounts in mass, so the mass in grams, of 65.60 and 9.44, and we figured out 24.96. This looks more like a 9. There we go. And then in L3, I'm going to have it calculate the number of moles, which is equal to L2 divided by L1. Shall we? Always a good idea to start by clearing your lists. Second plus 4, clear all lists, clear that out, start fresh, stat, edit. Get over to L1, and I'm just going to type for a second. Again, why are we doing this? Because it's going to be faster and more accurate in the long run when you get the hang of this. We're going to do it in other places in the course as well. I want you to be a lean, mean, problem-solving machine. All right, double check my typing. 65.6, 9.44, 24.96, 12.01, 1.01, and 16. So I go over here and very swiftly calculate the number of moles. How again? You know how to do it by hand. You're going to take the grams that you've been given, and that's going to be divided by molar mass, and that's going to equal the number of moles. So L1, be at the tippy top of L2. You got to be, or L3 rather. You got to be way up here. So I take second 1 divided by second 2, because my L1 and my L2 reside above that. I am not trying to insult your intelligence. I just don't know how much you know about your calculator. And that did not work out well at all. So what did I do wrong? Let's try that again. I did it backwards. L2 divided by L1. There we go. That's what I was expecting. Okay, so I've got 5.46 versus 9.35 versus 1.56. You do not write formulas that way. It is not C 5.46, H 9.35, O 1.56. We have to simplify these. And so to simplify these, I'm going to use L4. And that's going to be equal to everything in L3 divided by the smallest number, which is 1.56. Why the smallest number, you ask? Because I want a guaranteed 1, and everything else should come out in a multiple of that. If not, well, I may have to double the whole batch or triple the whole batch. Depends on what the numbers come out to be. So I'm going to scoot over and up to L4, take everything in L3 and divide it by the lowest number of moles I have, which is this 1.56. And I come out with something that looks pretty spiffy, 3.5, and it looks spiffy because I'm looking at that 1 down there and loving it, 5.99, and 1. So we're going to call that 6, and then we're going to have to double this whole mess. Why? Because I can't write 3.5 and 6 and 1 as subscripts. I need whole number subscripts. So I'm going to double everything so that this becomes 7, 12, and 2. So that means that my formula is C7. Just come back and match these up. C, H, and O. C7, H12, O2. And there we have it. Can you do it other ways? Oh, yeah. Yeah, you can. But fraught with danger. This is kind of slick and easy, and All right, so let the fast forwarding begin. You can skip right on through this and just take a gander at the very final answer, but this is a technique that is no longer in the course outline for the AP Chemistry exam, but it's still in your college textbook, it's still in college classes nationwide. It's not a bad thing for you to know how to do it. I'm just letting you know that if you love learning, you might want to listen. If you want to just skip forward, it's not going to harm you that much. So if you'd like to listen, we're off to the races. There is this formula that, again, is no longer on the formula sheet. It was up until the 2014 exam. And it's saying here the change in the temperature of the freezing point is equal to a constant, which has been experimentally determined, times a unit called molality. Now, you're familiar with the unit molarity, which is moles per liter. But molality is moles per kilogram of solvent. The difference is that molarity is temperature dependent, because as a solution heats, it often expands. As a solution freezes, it often contracts. On the way to freezing, I won't say at freezing. And then this, however, is a mass-to-mass ratio, molality is. But molality is also no longer on the formula sheet. So I'm just going to rearrange this and try to solve for what they want. We have a solution of 1.570 grams. Okay, so that's good to know. That's my mass. Of the compound, so my mass of solute, in 16.08 grams of camphor. I'm going to go ahead and change that to kilograms, and that's observed to freeze at a temperature of 15.2 degrees below the normal. Why below the normal, you ask? Because freezing is about molecules being attracted to one another through IMFs, and if you put a foreigner in there, an invader, however you want to think about it, then you're getting in the way of those attractions, and so it's going to always lower the freezing point because it's interfering with those IMFs. Then determine the molar mass, so that's what they want me to find, and apparent molecular formula of the compound. So the molar freezing point depression constant they have given me is 0.40 kilogram Kelvin per mole. So we start out here, and I want to actually rearrange this to try to solve for molality. So change the temperature of the freezing point over Kf is how I'm going to get started. And that's equal to molality, which is grams per molar mass of the solvent, over the kilograms of the solvent. And I did not say that right. That was solute. Almost made a big goof. So therefore, delta TF, I'm just going to cross multiply and put the kilograms of solvent over KF is equal to grams over molar mass, because that's what's equal to moles. So therefore, if I flip both sides, I will get molar mass over grams is equal to Kf over delta TF kilogram. Contemplate that for a minute. All right, so I can go on to say then, if I want molar mass, because isn't that what I'm after here? Determine the molar mass. So molar mass is now equal to, multiply both sides by G, Kf times the grams over delta TF kilograms, and I should have put solvent and solute just to keep you honest here. So let the plugging and chugging begin. 40 kilograms Kelvin mole, and then 1.570 actual grams used over the change, which was 15.2 Kelvin, and 0.01608 kilograms of solvent. And this kilogram is solvent. Okay, so my kilograms of solvent are out of there. My kelvins are out of there. And I come out with an answer in grams per mole. That is delightful if you are looking for a molar mass. So let's just work this little sucker out. You ready? I'll clear my calculator screen over here. 40 times 1.57, got my numerator, divided by, open a paren, 15.2 times 0.01608. My brain always wants to ignore that zero. And we come out with 257 grams per mole. Okay, I've answered the first part. Now, what else do you want? Well, remember, did we find an empirical mass up here? No, that's what we have not done that yet. So let's find the empirical mass, because that's the whole deal. This is the actual molar mass as experimentally determined. So we need to look at the empirical mass. So I'm going to call EM. Remember, it was C7H12O2. So that's 7 times 12 plus 12 times 1 plus 2 times 16. So that's how many of each atom and its rounded off molar mass. So that equals 7 times 12 plus 12 plus 32. I can do that part in my head. And I get 128. Is there a relationship here? Yes, there is. So molar mass is one half. Let's do it the other way around. This is an easier way for you to understand it. Empirical mass is 128. Molar mass was determined to be this 257. That's really close to twice, isn't it? Oops, wrong button. 256? Yeah, that's close enough for government work. So, therefore, molecular formula is twice empirical formula, or C14H24O4. Now, how did that work out? This was a point. Getting this was a point. And getting this expression, and your expression did not have to look exactly like mine. Getting that was a point. Okay, so next piece is when 1.570 grams of the compound is vaporized at 300 Celsius. Okay, I don't like 300 Celsius because I'm feeling, you talk about vaporize, you're talking gas law. So I feel a gas law coming on. So I'm going to change that to 573. How did I do that? I added 273 to 300 in my head. So it's 573 Kelvin, so that's my temperature. And my pressure is 1 atmosphere. And the gas occupies a volume of 577 milliliters. I'm probably going to want to change that to liters because we're in the land of gases here. I'm thinking gas law, and I'm thinking I'm going to have to use the ideal gas constant at some point. So I'm going to make that 0.577 liters as my volume. What is the molar mass of the compound based on this result? In other words, we're checking our work here in this experimental procedure. Okay, I'm not proud of this next part. But chemistry teachers all around the country have taught enough chemistry to know that often problems show up where you're taking ideal gas law and you're doing a density twist. So we've come up with this adorable little way to remember this formula. Molar mass kitty cat. Yes, I said kitty cat, as in feline. If you have a kitty cat, if you've ever observed a kitty cat, you may or may not have noticed that when a cat pees, it actually covers its pee, much more polite than dogs. They cover their own pee up with dirt. So DRT, dirt over pee, is the molar mass kitty cat. So if you need a visual, here's its body, here's its head, here are its whiskers. Any of you could draw a better picture than me. There are its cute little ears, and it's a happy molar mass kitty cat. Every good cat puts dirt over its pee. You're going to thank me for this. It translates into some fairly fast points on the AP exam. I know, quit laughing. 1.570 was my number of grams. 0.577 liters. Why again did I change it to liters? Because I got to multiply that by R, which is 0.0821 liter atmosphere mole Kelvin. Third time's a charm. There, mole Kelvin. And then what is the T? It must be in kelvins to make all this canceling work. 573 Kelvin. Kelvin, Kelvin. Liter, liter. So far I've got gram over mole, which is a good thing. And then when I divide all of that by pressure in atmospheres, if they'd given it to me in millimeters of mercury, which they did not, right? Didn't it come in atmospheres? 1 atmosphere. Made it easy on me. My oops. So now what's left standing is grams per mole. I always taught my students, do not bother reaching for the calculator unless you have it set up right, because you're just wasting your time, especially on the AP exam. So, therefore, molar mass is equal to all this mess. So I'm going to start with the 1.57 divided by 0.577. So that term is 2.72. Multiply it by R. Multiply it by 573. I'm not going to bother to divide it by 1 because the answer is 128. Now let's recap what we've done. They had us figure out, way back up here, an empirical formula, C7H12O2. Then they gave us a long way, but a scientifically sound way, to figure out the molar mass a different way, and it was twice that. Then you come back and you find the molar mass yet another way, using the density of the gas, and you find out it's back to 128. What gives? What is the deal? Well, that's what the last part's about. Briefly describe what occurs in solution that accounts for the difference between the results obtained in part B and C. In other words, why is this half as much? Well, there's a couple of different ways to think about it. Either the compound dimerizes. Oh. Now, that's a word you may not know, but I bet you know this word. Monomer. Think back to biology. Think about hydrocarbon units, and then when you put 2 of them together, you make a sugar. You put 3 of them together, you make another sugar. The first sugar was called a disaccharide. The second sugar was called first one was called a monosaccharide. The second one was called a disaccharide. And then you get polysaccharides, which end up being starches. So you've probably heard of this before. Monomer. And if you keep going, you can make, again, mono, 1, dimer. And you can make trimer, 3 units. And then once you go past that, you get a little tired of this, and you just go, it's a polymer. And poly is just a generic word for bunches. So either the compound is hooking up in pairs, okay, so it's dimerizing. So it's either forming a dimer or it dimerizes. You decide which type of verbiage you want to use. And the delta T F equals K M I thing, where I is the Van 't Hoff factor, which is something that is still in the exam, interestingly enough, without this application of it, where I equals 1/2. Let's pretend that word looks like where I equals 1/2, because you can have half ones. Since the molar mass is twice that of the gas phase. In other words, in English, when you take this stuff from the gas phase and you bubble it into water, it forms pairs with itself in water. It forms, again, dimer is the word we use for it. It forms a dimer. And so, in other words, that pair is behaving as if it were one molecule. The flip side of this argument, equally valid, which may have occurred to you, and you're going, that's not what I was thinking. I was thinking something else. I was thinking that the compound dissociates in the gas phase. So the dimer that exists in the liquid phase, like think disaccharide, sucrose is your favorite disaccharide. Perhaps, I'm not saying this happens, okay, using an analogy here, but perhaps if you vaporize it, then it becomes monomers again. So Or you could state that the compound dissociates in the gas phase. In other words, A becomes 2 of something new called B. But it was a point for either explanation. Now, is that the best example of a current stoichiometry problem? Oh Lord, no. Let's go on to a better example of what's going on these days on the exam. It's a great problem, just not the best for the current day. Current being today's date, which is, I don't know the exact date. I'm in August of 2014 somewhere. All right, so let's look at this one. Clear my calculator. I'm going to clear my list just because that's good protocol, so I don't accidentally get confused later. Now what do you want me to do? This is moving on into this century, and just for fun, this was a 10-pointer. Answer the following questions about beryllium oxalate. Okay, you don't have to memorize a lot of polyatomic ions anymore, but when we did, I had a favorite, and it was oxalate. So this problem made me smile when it came out. Calculate the mass percent of carbon in the hydrated form of the solid that has 3 waters of hydration. Dot waters, I lovingly refer to them as. The technical name is waters of hydration. All right, so percent, mass percent of carbon. That just means part of carbon over whole of compound, and with regard to mass. So percent carbon by mass is carbon's mass, and there are 2 of them. 2 times 12.01 over the total mass. It's going to take a little room. Beryllium. Don't have that one memorized. Even I don't have that memorized. 9.01. Plus 2 of the carbons at 12.01 apiece. Plus 4 of the oxygens at 16 apiece. Plus 3 of the water molecule I've given up and memorized is 18.02. If you need to do it with the hydrogens and the oxygens, there's no shame in that. And then this whole mess is not the answer. If they ask you for a percent, they really want a percent. So you've got to multiply by 100% to get that. So, shall we? I can do 2 times 12.01 in my head. So that is 24.02 divided by, open a paren, 9.01 plus 24.02 again, plus 4 times 16 is 64, plus 3 times, can't do that in my head as easily, equals 0.159, but multiply by 100, and you come out with it in something more like a normal percent. So let's call it 15.9, 3 sig figs. Why am I going with 3 sig figs? Do I have a reason? I do not have a reason. So when in doubt, go with 3. So 15.9%. If you could do that, you've earned 2 points. Nope, just 1 point. 1 point right now. I lied to you. Just 1. So when heated to 220 degrees Celsius, it dehydrates completely. In other words, it loses those dot waters. So that's going to come off, this part right here, as represented below. So here are my 3 waters over here. If 3.21 grams of this entire trihydrate, is heated to 220, calculate, 1, the mass of this formed. All right, so I'm just going to start with that balanced equation. I'm just going to rewrite it so I can write on it. So BeC2O4, you would not waste valuable time doing this on the AP exam. Now you can do stoichiometry any way you like, as long as you're good at it. I am not trying to change you. If you are not broken, I am not trying to fix you. This is just my way. I get a balanced equation. I put in the fact that this was 151.08 because we had figured that out before. And then this is 97.03. Just getting the molar masses. And this is 18.02. So pause me if you need to go verify those molar masses. I'm going to scoot down because I need a little more room. All right, so that's my mole to mole then is, this is balanced, right? 1 to 1 to 3. So that's my mole to mole ratio. And the amount that I'm going to get started with, not ATM, AMT, amount, is right here. What did they give me? They gave me 3.21 grams of the hydrate. 3.21 grams divided by 151.08 is what we had figured out, is equal to 3.21 divided by 151.08 is 0.212. Did I have a leading zero in there? I do. It's my bad habit. Don't know why my brain rejects that zero. Mole. So isn't this then also going to be, well, I'll put number of moles up here. Make it a little easier on you. 0.0212. Just bringing that up. So isn't this also then in moles, because it's also got a coefficient of 1? 0.0212. And then what would this last one be? What's sitting in my calculator of 0.212 times 3? It's going to be off in the last digit, but that's okay. We give you a little wiggle room. 0.0637. Now I know moles of everything. All that's left to do then is actually answer the question. So now I already know how many moles, so let's just multiply that by the molar mass and we can find the mass of the beryllium oxalate that we seek. So apologies, here goes. 97.03 times the fact I have 0.0212 moles gives me 2.0 to 3 sig figs, which is what looks good here. Let's go with 2.06. So therefore, 2.06 grams of the beryllium oxalate is formed. And there you have it. Happy dance. All right, so now what do they want me to do? They want me to do the volume of the gas, water vapor, released, measured at 220 degrees Celsius. Well, we know better than that. We know that's got to be in Kelvin. So 220 plus 273, I can even do that in my head, is 493. So we just use our good buddy, the ideal gas law, Pivnert, if you prefer. So PV equals nRT. Therefore, the volume is going to equal nRT divided by P. And it's a plug and chug fest from there. So I have my how many moles? 0.0637 times my good buddy R, liter, atmosphere, mole, Kelvin, and my newly determined 493 Kelvin, and all that mess is divided by atmospheres. Oh, but phooey, they gave me a pressure, but they gave it to me in millimeters of mercury. Not to worry, not to worry. 735 divided by my good buddy 760 in millimeters of mercury will make the relationship that is now going to be atmospheres. You can do all the canceling if it makes you happy. I'm just way too lazy for that. You know me by now. So, therefore, this volume of water is going to be equal to, clear my screen, 0.0637, get that in there correctly? Yes, I did. Times, you can use your R, or you can type it in, it's your call, depends on if you've saved it or not, times 493. I should have said stored it, that's better than saving it. That's the right calculator lingo. So there's my numerator, divided by 735, divided by 760. Make sure it's in parentheses though, otherwise that 760 pops back up to the numerator. And we come out with an answer of 2.6. Again, let's call that 7. So 2.67, and all this canceling leads me to liters as my only unit left standing, which is a good thing if you're asking me for a volume. And voila. So far, so good. Let's see what else they're going to torture me with. Oh, a whole new scenario. Okay, so this scenario is starting out with a new reaction. So I'm going to change my pen color for you and say, all right, let's figure this out. We've got a 0.345 gram sample of anhydrous beryllium oxalate, which contains an inert impurity, and it was dissolved in sufficient water to produce 100 milliliters of a solution, and then a 20 milliliter portion. Okay, think about that for just a second. That's going to be 1/5 of the total, right? Right. And that was titrated. I'm getting a little picture in my head of a big burette and a little beaker or flask underneath it, and drippy drippy. And KMNO4, though, that's got cool purple stuff. If you haven't done a lab with that, perhaps you will before your course is finished, but it's uber purple. And you get it on your skin, it makes you brown. So hydrogen peroxide is the best way to get that off, but this is a classic in terms of oxidation reduction reaction lab stuff, so I hope you've done one of those. And the balanced equation, thank you for giving me the balanced equation, by the way, has occurred as follows. So I have a 16 to 2 to 5, blah, 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 blah ratio. All right, so let's actually read something they want us to do. The volume of the potassium permanganate, the 0.0, I should say, 150 molar, that much of it that required to reach the equivalence point was 17.80 milliliters. I'm going to switch to purple because this stuff is purple, and that's way more fun. So it's purple stuff. And then, what else? Oh, that's all they tell me. Okay. And then they ask me on part I, identify the reducing agent in this reaction. Okay, this is not going to be worded this way anymore. It used to be back in the day, but reducing agent is that which is itself oxidized. So it would just say identify the species oxidized or something like that. Or reactant oxidized. In the titration reaction. So let's go back up here to our reaction. Oops, sorry, I went too far. Making you dizzy now. And who is oxidized? That means their oxidation number goes up. Well, H plus can be a candidate, but in this case it is not. It's going to be either the permanganate, which starts off with that Mn as a +7, because 4 negative 2's for the oxygen is -8, but we have a total negative on the charge. The only way to make that work algebraically is for Mn to carry a +7. And so that means that that's going to be reduced over here clearly to this 0.2. So my only critter left standing is my oxalate ion. So C2O4, do not forget the charge. If you wrote it as C2O4, you'll get 0 points for that after all that thinking. So that is the species oxidized, or you can say is oxidized. And then for the titration at the equivalence point, calculate. Okay, that's more what I expected. Calculate the number of moles of each of the following that reacted. So first we want the MnO4 minus that reacted. So that's simply because it's in solution, the molarity. I'm going back to my purple for this. The molarity, which is going to be 0.0150 moles per liter. That's an O. Moles per liter times how much of it? 17. Oh, I've circled it. 17.80 milliliters. And so I get an answer in millimoles, but that's okay. So 0.015 times the 17.80. It is okay to answer in millimoles, by the way. So that is equal to 0.267 millimoles, and you could leave it at that, or you could go ahead and convert it to moles if you prefer. So that would be 2.67 times 10 to the -4th. Think about it. Got to move that decimal one more time. You know, milli is moving it 3 times, and so -4th moles. Either one of these is correct. And we would be proud of you on the AP exam. So what are they going to do to me next? Okay, next they want us to calculate the concentration of the oxalate ion. So let's go up to the balanced equation that they were so kind to give us, and let's figure that out real quick. All right, so we already know, just from the fact they've balanced this equation, that we have a 2 to 5 ratio going on here. And we just figured out that we had the 2.67 times 10 to the minus 4 moles of permanganate. So 2 goes with 2.67 times 10 to the minus 4 mole. And so I'm going to clear my calculator here. So 2.67 second EE minus 4 would be divided by 2, because that's the coefficient on it right there. That's why I bring my 2 down so I can see it nice and clearly. And then multiplied by 5. That's the multiple ratio going on here. So that would be 6.6, let's call it 8, times 10 to the minus 4th mole. So it's okay to just write that down, to just say the 2.67 times 10 to the minus 4th mole times this idea of, well, I should say divided by 2 and then multiplied by 5. And you can put the rest of the dimensional analysis in there that makes you happy, or you could simply say see above. Either way, you're going to come out with an answer of 6.68 times 10 to the minus 4 moles. So my students would have said C above underneath that and focused in on blocking that so that it was easy for the reader to look up there and see that. All right, what else do they have in store for us? Calculate the total number of moles of oxalate that were present in the 100 milliliter of the prepared solution. All right, well, that's not terribly evil, because if you think back, we already said that we used 1/5 of the sample, right? So we used that 20 milliliter portion, which was 1/5 of the sample. So won't you have 5 times the number of moles? So 1/5 of the original sample was used, or titrated is a better way to say it. Therefore, 5 times that number of moles they just had you figure out. Let the problem lead you. 6.68 times 10 to the minus 4 mole. So multiply by 5. And that means there were 3.34 times 10 to the negative 123 moles of C2O4 minus 2 minus in the sample. Simple proportion. Not all of chemistry is hard. I know. One day you're really going to believe me when I say that. All right, and then all of this to ultimately figure out the mass percent of the beryllium oxalate in that impure 0.345 sample. All right, so we're in the home stretch. The final thing, calculate the mass percent of the beryllium oxalate in the impure 0.345 sample. So we've done all this work and we have arrived at the moles of oxalate. So that's probably where we ought to start. So let's go with our 3.34 times 10 to the minus 3 moles of the beryllium C2O4 oxalate. And then what should we do with that? Well, when in doubt, find the number of moles of something, anything. So multiply that by its molar mass, 97.03 grams per mole. We'd figured out earlier up at the top. And all of that is divided by, so that's the number of grams, agreed? Moles cancel. So that's the grams that we actually have determined are in there. I put an extra 0 in that time to make up for all those times I leave one out, huh? Grams sample times 100%. If you better put that percent on there too. They're getting kind of picky about that. Well, so let's see what we get here. Let's just clear my screen. So 3.34 second EE minus 3 times our 97.03 molar mass gives me the grams that we recovered here, divided by the fact our sample total mass was 0.3, so I typed 345 times 100. And we come out with 93.9. 3 sig figs good? Yep. 93.9. Do not leave that naked. Be sure you put the percent on there. Now, that's a marathon. That is not an easy problem. If you did that all by your lonesome, then you are sitting pretty and you can relax about stoichiometry. If you struggled through and got only half of it done, you're still well on the road to doing well in this course. So do not beat yourself up. It is really, really difficult to work such a long marathon type problem and get every single morsel correct. But if you're getting more than half correct of the points, then at this stage of the game, you're doing good. If you're reviewing this in the spring, I would like to see, if this was a 10-point problem, I'd like to get you up closer to like 7 out of 10. But hey, 5 is not shabby. 5 is gonna work well for you. All right, so shall we do another? Shall we dare to do another? This is another 10-pointer if you're keeping track, if you like to keep score. Nothing wrong with that. I like to do that too. All right, so here we go. We've got to, let's see, we have an iron 3 oxide that can be reduced with carbon monoxide according to the following equation. And they gave us all the formulas, yippee skippy, so we don't have to worry about any of that. Then they tell us that there's a 16.2 liter sample of CO at, oh, do you feel Pivnert coming on? Look at that, there's a pressure. At this pressure, so that was a volume, and we know better than that 200 degrees Celsius. We know that's got to go to 473 Kelvin, so you might as well just do it now. And that's going to be my temperature. So I've got a V, a P, and a T, and that's combined with a mass of the iron, what's that going to be, 3? Yeah, the iron 3 oxide. So sure enough, you could have written this part, couldn't you? How many moles of carbon monoxide are available for the reaction? This is sort of a, if you can't do stoichiometry, maybe you can do gas law's pity point moment. So I'm looking for the moles of CO, and that's going to be equal to PV divided by RT. And now let's just plug and chug that. 1.50 atmospheres, 16.2 liters. Feeling pretty good about this. 0.0821 is what I use. Liter, atmosphere, mole, Kelvin. It's okay if you use 0.082106. You're going to come out really, really close to the same ballpark as me. And that was Kelvin. And so atmospheres cancel. Liters cancel. Kelvins cancel. A 1 over 1 over mole is mole. And since mole is what I seek, I'm feeling pretty good about that. So, shall we? 1.5 times 16.2 divided by 0.0821 and times 473. Enter. All right, so 0.626, correct? Yes, 0.626 moles CO2. Well, CO2, sorry, carbon monoxide. The stuff you never want to breathe. All right, easy enough there. By the way, that's 2 points so far. You got 1 point for just setting this up correctly and 1 point for actually putting the numbers in your calculator correctly. So what is the limiting reactant for this? And justify your answer with calculations. Now we've got to go back and look at this equation. So we know the moles of CO. I'm going to rewrite this equation where I can actually kind of look at it a little bit bigger. So Fe2O3 plus 3 COs yields the 2Fe and the 3CO2. All right, so what we know right now is that's a 1 to 3 ratio. The other thing that we know right now is that we really in true life have 0.626 moles. So what I can do real quick is take what's sitting in my calculator and divide it by 3 and say that this needs to be at least 0.209-ish, or else it is the limit, the iron 3 oxide. So let's figure it out. How can I do this? Well, I've got, they gave me the amount, didn't they? Yeah, they gave me combined with grams. Okay, so easy enough. So the 15.39 grams of the stuff divided by its molar mass. That's 2 irons at 55.85 apiece. And you know the oxygen is 16 by now. And what do we have that come out to be? 15.39 divided by 2 times 55.85. Oh, I'm going to do this way. Plus 48. I can do that in my head. And we come out with 0.96, let's call it 4. Oh yeah, we had plenty. Right, I didn't miss a 0 anywhere, did I? Oh, I did. See? You think I could conquer this habit. Try that again. 0.0964. It's a very bad habit. So, do I have enough? No. I needed at least 0.209 based on that mole-to-mole ratio of 3 to 1, already determining that I had this much of the carbon monoxide, dividing that by 3. Even in my head, I know it's got to be coming out around 0.2-ish. Yeah, not going to happen. Not going to happen at all. So, this is my limit. So this is now a lie. That's not how much is going to react. How much is going to react? Well, 3 times this. So 0.289 is what's really going to react, and that's what they want to know. What is the limiting reactant for this? It is Fe2O3. Fe2O3 is limiting since 0.0964 times 3 moles of CO needed equals 0.289. Thus, therefore, it limits the amount of product. Plural, formed. The work is above. See, work above is always a good idea. So anyone who is following what you're doing, and those are the people who are scoring your papers, can figure this out. So the limiting reactant for the reactant, justify your answer with calculations. We did this. That's moles. Probably should label it. Of our iron, Fe2O3, and this was our mole, clearly, of CO in the table. All right, so then, based on that, how many moles of iron then form in the reaction? Well, if this is a 2, that would be a 3, so I have a 1 to 2 ratio, so therefore I need twice of that amount, so therefore I need 0.193 moles to be formed, or produced if you prefer that. So 0.193 moles of FeS formed. And what I would do is draw a little arrow up here and block that off. Since this is your limit. Right, so that was worth the point. Now, let's see what happens here. In a reaction vessel, 0.6 moles. How kind that they gave it to me in actual moles, not making me figure that out. And 0.3 moles of phosphoric acid are combined with deionized water in a final volume of, okay, there's the evil part, 2 liters. And the reaction represented below occurs, so they gave me that. I'm going to rewrite that because that's not enough room for me to work very well. So 3BaNO3 twice plus 2H3PO4 Ba3PO4 twice and 6HNO3. Old habits die hard. I want to see a 3 to 2 to 1 to 6 ratio staring at me at all times. All right, so calculate the mass of the BaPO4 blah, blah, blah formed. Okay, see this little and right here? That's trouble, because that means that you're in the land of limiting reactant. But it's easy land because they gave you the moles. So my moles of the barium nitrate was 0.6, and my moles of the phosphate, or phosphoric acid rather, is 0.300. And these are easy to work with even in your head. Pick one. If 3 goes with 0.6, I'm just going to take 0.6 divided by 3 in my head and get 0.2, and then I would need 2 times 0.2, so I would need 0.4, and that's not enough, right? 0.3 is not 0.4. You don't have enough. So we know that this is the limit. I could do it the other way around. I could have started with the 0.3 over here and gone, okay, 0.3 divided by 2 is 0.15. And so 0.15 times 3 is 0.45. Oh yeah, I got plenty. So I've got 0.6. So either way, this is my limit. So this is a lie. I'm not going to be using that much. Again, I'm going to take the 0.3, and that goes with 2, so that's 0.15. Multiply 0.15 in my head by 3. That's 0.450 used. I can also say, because this is easy numbers, 0.150 excess. They didn't ask me, but who knows? It may come up later. It's worth jotting it down while I'm thinking about it. All right, so what do they want? They want us to calculate the mass of the barium phosphate formed. Okay, so here, if 2 goes with 0.3, therefore, not very pretty, therefore 0.150, or half of 0.3, is formed, and 3 times 2 is 6, so 0.900 moles of that are formed, just in case they ask me later. Again, while you're there, you might as well spend that extra second thinking about it. The bad news is they did not give me the mass of the barium phosphate, so I need that mass because they want grams, or mass implies grams. All right, so I've got 3 bariums. Looking at my periodic table, 3 times 137.33 plus the phosphate. That's 2 phosphates. So answers plus 2 times, and phosphate is 30 point, or not phosphate, but phosphorus, 30.974 plus 8. Why 8? Because 4 times 2 is 8. 8 oxygens. 8 times 16. Close all that mess. I should come out with 602 if I did that right. Yep, 602. I know it shocks you. I actually work these problems before I start recording. So 602 grams per mole. And so that number sitting there by the fact I made 1.50 moles. So 0.150 moles formed times not 6.02, that's a habit, isn't it? 602 grams per mole of phosphate, barium phosphate, equals 90.3. 3 sig figs enough? Yeah, 3 sig figs looks good. So 90.3 grams of Ba3PO4. Box your answers. For the love of God, box your answers. Old people with bad eyesight are grading your papers at the reading. All right, so oh, I missed something. No, that was right. So what do I need next? What is the concentration of the nitrate ion after, prepositions are always troublesome, after we reach equilibrium or completion? Well, this is an easy question. Often the easiest question is at the bottom of the question instead of at the top. What's the concentration of the nitrate ion? You know what? Nitrate didn't react in this. Look at this. If you wrote this net ionically, these nitrate ions are spectators. So how many nitrate ions did you have? Well, 6 on both sides of the equation, because you had 3 of the barium nitrates, and each one of those had 2 each, and 3 times 2 is 6. Or you can look over here and say, I have 6. But either way, the final concentration of nitrate is the same as the initial concentration of nitrate. And so pick something and start. Well, this is where you should start. because that's how much is really there, including the excess. See, this one is based off of my limiting process. So this one is the truth. So I'm going to start with that 0.6 mole. So the concentration of the nitrate is equal to the fact that I had 0.600 mole of it at the start, and it's times 2 because it was housed in barium nitrate. So that's where that 2 is coming from, right there. So I really had 1.2 moles of it, but I had a total volume of, don't be tricked by that, I thought we had that somewhere. Oh, sorry, I went too far. 2 liters right there. 2 liters. 2.00 liters. Comes out in moles per liter, which is what a concentration should be. And hey, so you can write it that way. You can write it this way. Concentration in the square brackets mean mole per liter. You can write it 0.600 liter mole minus 1, mole liter minus 1. That's probably better. There's all different kinds of ways to label it properly. Just label it. Personally, I think the brackets are the easiest. All right, they actually could have easily made that part 1, but they did not. So they made it toward the end. So it was kind of generous, yet a little bit twisted. All right, so I hope that worked out well for you. And you know what? That concludes this session. Thank you ever so much for your kind attention. I hope you have a great rest of your day.